Hi, now we're going to look at fossils and the process of turning once modern life into fossils and making it part of the sedimentary rock record. So the question is how you change this modern life here, current life beneath the surface, into ancient life that's preserved in rocks for millions of years and then eventually can be discovered by a human and studied. Well, how life becomes a fossil is, first of all, you need at least about 10,000 years to really call it a fossil. There's nothing special about that period of time other than when it's less than 10,000 years old. You basically just call it a remains of past life, and then after that it becomes a fossil. You also need rapid burial. Now this is crucial. So you need some kind of burial that occurs really fast before the animal has a chance to break down and disintegrate. So something like a flood or a volcanic eruption that covers it in lava or a landslide. And so what is key there is that you remove the oxygen, so it becomes a low oxygen environment, and that's going to help prevent the breakdown of material and the disintegration of that animal and help preserve it. And then the third thing that you really need to help preserve it is hard parts. So teeth, bones, exoskeletons like this particular critter, which is a trilobite, and these were quite common in the Paleozoic and have since gone extinct, but this little guy has an exoskeleton, so that is one big reason why it was preserved and why we can see it today and study it. So hard parts preserve well, teeth, bones, exoskeletons like we just saw, and this jaw here that you can see, this is from a quarry in Wyoming, in eastern Wyoming, and it's part of a jaw, and you can see some teeth of what could be an ancient rhinoceros-like or horse-like animal. So how do we get fossilization? What exactly occurs? You can do this in a number of different ways. The first way that we'll look at here is permineralization, which is a process where minerals fill in empty spaces around the original organic material that disintegrates. So that kind of, decomposes away. But minerals come in and they, through water, so again, something like getting it buried in a groundwater or something, coming in there and depositing minerals in there. And some of the common minerals that you can get is pyrite, and that's iron sulfide. Right there, there's the chemical formula. So if you've seen like pyrite fossils, pyritization of ammonites and things like that, it looks almost like it's got a gold structure to it, but pyrite is also known as fool's gold, so it isn't real gold. It's iron and sulfur, as you can see there from the formula. Also, you can have silica, so quartz, in a variation, probably a cryptocrystalline quartz, like a chalcedony, will come in and move into those mineral spaces and fill in that. And it kind of preserves the original look of the once living creature. And a good example here is this petrified wood. So what people call petrified wood is actually permineralized wood. And so that's with silica coming in a very cryptocrystalline type of way. And because it's so small, crystalline, it can preserve that pattern of the tree rings and everything. Another way to make a fossil is through compression. So compression fossils are flattened between layers of sedimentary rock, and we're going to be doing that in a little bit here with our flower pressing. So we're going to not really make a fossil, but give you the idea of what that process is like. In an actual fossil in the natural world, it's compressed or flattened in layers of sedimentary rock, and then chemical reduction occurs, which is actually a gain of electrons, but that chemical reduction will geochemically alter that once living form. And so it still has original material, but it's geochemically altered. So there's actual chemical reactions going on so that that's no longer quite the same plant as it once was, but it still does have that original material and more importantly the original pattern so that you can recognize it for what it is or what it was. So this compression fossil is fairly common with things like plants, fungi, algae, ferns. Plants and ferns do really well because their leaves are already kind of flat, and so if you compress it kind of parallel to that, you can get really good preservation because it's flat already, and so versus if you do something like an animal that's really 3D, it's going to be a lot harder when all that gets flattened to one plane. So that was a little bit about how fossils are made. Finally, how else are fossils important? I mean, other than they're really scientifically important and they're fun to find and fun to look for, how else are they important? Fossil fuels, of course. Fossil fuels are called fossil fuels for a reason. So one type of fossil fuel is coal, and that is a compression fossil, basically, of many, many plants over millions of years of time. So it's compressed to the point where, like in that previous slide, you could tell it was a plant. It is no longer recognizable necessarily as a plant, and some coal is compressed so much that it actually becomes a metamorphic rock. And it's not even a sedimentary rock anymore. So you're definitely not going to be able to identify species of plants that created that coal. But it is a source of energy. All these plants over millions of years of old swamps, and it's responsible for our modern world. That's a very important source of energy. Another important source of energy is another fossil fuel of oil and gas. So in this case, small fossils such as microbes, not dinosaurs. So the gasoline that you use did not come from dinosaurs. It most likely came from microbes, so very small fossils. And they form compression fossils over time. They went into a geochemically altered state, so it's carbon and hydrogen. It's no longer it's still the original material, the original carbon and hydrogen, but it's now in a geochemically altered state, and it's in like a liquid or a gas form. So this little diagram here shows you some of the coal bed methane, not quite as compressed up there towards the surface. And then down below you have a conventional gas. Gas is lighter, of course, than oil, which is liquid. There's the conventional oil. And then down even further than that is like what they call tight sand or gas or oil-rich shale. And so that would undergo even more burial under there. And what is very important for getting oil and gas to the surface and using it is a trap rock. So there needs to be, and that's that light gray rock in that diagram there. It's a trap, and it will keep it there because otherwise oil and gas is very light and it will rise to the surface and evaporate, and so you can't use it. So you need to kind of trap it there until you mine it. So that's a little bit about fossilization. Now in this next section, we're going to take once living material. So if you're at home and doing this remotely, you can find things like blades of grass or a leaf that fell down from a tree, something like that, and press it. And so we're going to kind of approximate the process of compression fossils, even though we're not going to make a fossil because we don't have to wait 10,000 years and we don't have that kind of pressure to put on it. But we're going to approximate it with that. You can also get flowers if you want to sort of dedicate a flower to pressing. You can do that as well and make some interesting designs. So let's go ahead and do that. Okay, well now that we've had a little bit of time to let the glue dry between our layers, and you can, again, just to review, we've got different layers, which indicates like different material. You could have calcite, you could have sandstone, and then they were cemented with glue. In a natural case, the three types of cement, as you know, are silica or calcium carbonate or iron. Now what we're going to do is kind of approximate a fossilization process. It's not going to be completely like a fossil because it's just being pressed, but flower pressing and plant pressing is a way that you can kind of approximate this, because you will get, we will do the compaction part and the compaction part and the rapid burial. So we're going to pretend like a landslide or something came and buried these very quickly. Now, if you're doing this at home, you don't have to go out and get flowers. I have a couple of flowers that we got and they kind of died a while ago. You can just use anything outside. You can use like leaves of grass or a leaf that fell down from a tree, something like that. You don't have to necessarily go out and get flowers for this. Now, I'm going to place them here, approximating what a river or a stream would do if it deposited these dead pieces of material. And now, I am going to approximate a landslide, rapid burial. There. Now, we haven't had the compaction process yet. I'm going to put this in an kind of an undisturbed corner of the house. So you might want to find something like that, because ideally you will press these for a month. Now I know we don't have that much time. So if at least you do it for like a day or two, you can get the idea. And then what I'm going to do, just to be safe, because I'm using a book, you could use a big book, the biggest book in your house you can find. Maybe it's your parents and you don't want to accidentally get glue on it, just in case the glue hasn't dried. So I'm going to put an extra layer of cardboard down, just in case. Okay, that's, again, some more rapid burial of these flowers. And then comes the compaction. And that compaction, if you remember that crumpled up tissue that I had, that will also compact that. So I'm not going to throw it down because that'll be a little bit too dramatic, but there we go. And we will just wait and see the results of our compaction fossil.